Hello everyone. Today I'm going to be talking to you about space-based observation and orbit determination, also known as SBSS. This is something the Air Force has looked into for a couple of reasons we'll talk about. It lines up really well with what we learned in the first half of the class, especially with the things related to orbit determination. And there's a couple interesting techniques that we'll talk about that are sort of variations on themes we went into. All right, so why would you want to do space-based surveillance of space, or space-based space surveillance? Main reasons are you have a higher time on target. Think about for a satellite, especially one in a sun-synchronous orbit, you have 24 hours of observation every day, as opposed to, say, 8 or 12 of complete darkness, also not affected by weather. This contributes to a higher detection rate. That and also the proximity and having no atmosphere to search through means that there's a much greater resolution for optical systems in space. The most important reason, the reason the Air Force is so interested in it, is there's a potential for better geo-tracking. There's currently a lot of gaps in the coverage of certain geo-bins due to limited resources that the Air Force has. They're really interested in putting an optical telescope in space, specifically to track geosatellites. Sort of incidental to that mission is there's a better chance of detecting very small particles on the order of a millimeter to 1 centimeter. And as that subpoint says, that you're never going to catalog every one of those objects, especially from one space-based platform. That data would be used to inform theoretical models that could potentially save lives of astronauts and a lot of material damage too. These are a couple of the current vehicles. There's Canada and the U.S. both operate some. This in the lower right corner is the only one of these I think that's currently active. It's the SBSS Block 10 satellite operated by the Air Force. You can see the 2-axis optical instrument there, the sun shields and solar panels. That's nearing its end of life, but it's been attempting to catalog all the geo objects that it can. All right, so how does SBSS work? Well, for reasons I'll go into in just a minute, you want good relative motion between the spacecraft and the target. Two things in the same orbit. That's not going to give you a good solution based off your observations. In addition to that, you need a good idea of your actual observatory orbit and position. This is easy in low Earth orbit and medium Earth orbit to an extent, and that's because of GPS. It's not as easy in GEO, and that's because GPS doesn't reach up that far, and you have the same problem as tracking the GEO resident space objects in the first place. As David Volato found, a 10 to 30 meter along track error grows to 200 to 300 meters in GEO. That's not good. All right, well, how good is SBSS? So Volato, of textbook fame, did simulations to validate the Air Force program. He was aiming at producing IOD and OD solutions for geo-resident space objects, so what the Air Force is really interested in. To simulate this, he generated look angles from 3 separate TLEs for 3 different objects and studied the convergence of Gooding's method of IOD, which I'll talk about right now. All right, so Gooding's algorithm. It's something a little different from what we learned in class. It's something called a range iteration method. So in addition to the standard inputs we're familiar with, the Q-hats, the R vector, and the actual observations and times, it requires you to guess at least 2 slant ranges. And this is so that the method can take advantage of a robust Lambert solver. Gooding talks about how his Lambert solver is, I think his words were, it never breaks. And this is the ISO-Gooding solver that we're using off the file exchange. And so it iterates on those guesses. I'll talk about it with the pseudocode here. Here's the pseudocode for Gooding's algorithm. You can see some of these inputs are very similar. The R's, in this case, would not be the R of the surface observatory, it'd be R of the spacecraft, time of the observation, and lambda, which is actually the unit vector pointing towards, or for the slant range. Next, this is different from our methods. We assume a value for the slant ranges, the 2 outer ones. And this effectively gives us Lambert's problem. We've got two r vectors backed out from here, and we have the times. So the next thing is to generate an estimated orbit by actually using that Lambert solver, employing it to give us two v vectors. Those conveniently are actually derivatives that we can use to iterate on those initial guesses, and so that apparently has a very, very high success rate in actually providing an orbit from observations. All right, so this is a table that Volato generated based on the performance of that algorithm and his simulated conditions. In this case, it's a low Earth orbit observatory looking at a geo object. Here's the TLE for the geo object with the actual orbital parameters down here. You can see semi-major axis, I think divided by 2, is 42,000 kilometers, roughly, which is expected. And he's highlighted the solutions that are closest. This is iterating just on 3 sets, and this is doing some statistical stuff. It did pretty well determining an orbit, and in his conclusions, Volato points out that this would be more than enough to get initial orbit determination, sense for later use. It's matching some parameters very well. Right ascension, especially, admirable performance for the solver on this almost circular orbit. So the thing is, though, is that as you start to go higher with your observatory, this is in a GPS-like orbit, you start to lose a little bit of that, and a lot of that has to do with low observability. You're not getting as many observations just because of the lower period of the higher orbit that the observatory's in. And you can see nothing really came close on semi-major axis to these guesses except for this set of 3 observations. None of the statistical stuff really did that great. Taking a look at this set of observations for a telescope co-located in GEO with the RSO, it initially looks pretty good. The inclination, everything agrees. You're coming up with the same thing no matter which data set you use. All of these semi-major axes are very, very close. All these ECCs are very close. Argument of parity is even well within, a couple exceptions, very, very close. The problem is that this is actually a degenerate solution. And this actually is representative of the telescope orbit rather than of the GEO orbit. And now you can think of that like the telescope is observing something that's phased in its same orbit rather than observing something that has actual relative motion. All right, and then so if for this other TLE, however, the inclination down here, the actual inclination is about 14 degrees compared to about 1 for the simulated SBSS orbit. And that gives a little bit of a better performance, at least a more predictable performance in terms of how there's a little bit of variation here. So we're not getting suspicious of that answer. And it does provide a fairly good solution in terms of semi-major axis, which, according to Volato, is the most important thing for especially initial orbit determination. Okay, so this is what Volato really has to say about the performance of the SBSS. It does give the best performance, as we saw in LEO orbit, and that's giving about 150 meter along track error for that actual GEO RSO. The 2 sigma errors, or the standard deviations, go to about 1,200 meters along track for the MEO and GEO, just for the location of the actual telescope, not for the object that it's observing. This does introduce quite a bit of error, however. And then the GEO orbit, as we saw, is generally bad. That low relative motion precludes good IOD and OD because it gives a lot of degenerate solutions. Apparently, what helps with that is augmentation with ground-based observations. That's fine. It's just that the main goal of space-based observations is to reduce the need and the workload of those ground-based optical telescopes. All right. So I hope you all enjoyed that presentation and learned something about maybe interesting application of the angles-only stuff we learned at the beginning of the quarter. Here's Gooding's paper. I encourage you to look it up. It's got a cool thing. His algorithm's mostly there. Volato's paper, and then a lot of these are sources for images and just general concept of operations of these spacecraft. Anyway, have a nice break.